Sweet. So we are going to go over the different types of signals. So like heterotopic, homotopic, enantiotopic, diastereotopic, all that jazz. So I first like to break them down into, okay, thank you so much for that. Homotopic versus heterotopic. So from the names, do you have any idea what homotopic and heterotopic could mean? And again, your answer can be as general or as specific as you please.
I remember from SI hetero. Well, no, that's heteroatoms. Never mind.
But I'm glad you're connecting dots and thinking of things. That's really good. But okay, so let's break it down a little bit, right? So homo and hetero just means same and different, right? And
Yeah.
specifically when we're talking about signals on NMR, we're going to say same signal and different signal. And that's the like super bare bones definition kind of, right? So homotopic describes the relationship between any two hydrogens that are part of the same signal. Whereas heterotopic defines the relationship of two hydrogens that are part of different signals. These are both super, super general umbrella terms, and enantiotopic and diastereotopic are more specific terms that fall under these categories. Before we go into them, though, I just want to make sure you guys know these words are like comparison words, right? So you can't look at one hydrogen by itself and be like, okay, this is homotopic. Right? One signal and be like, oh, this is heterotopic, because they're not like definition words, they're comparison words. So you can only use them when comparing different hydrogens or different signals. Any questions about that?
So far, I'm getting it.
Okay, good. I love to hear it. All right, so when we have an enantiotopic, I know I'm color coding it, so this question is going to be, sorry, spelling this is really difficult, so I can't write and spell at the same time. But so I've already color coded it, so I'm not going to ask you what category you think each one falls under. But essentially, enantiotopic is a very specific type of homotopic signal. So this is essentially when the same signal with the same chemical properties and what we need to look out for is potential chiral centers, which I denote like that because in Orgo 1, chiral centers were denoted with just a star. But if it's a potential chiral center, I like to give it a star and a P on top. We can go over exactly what that means in a second. So let's look at an example like so, right? Actually, let's make something that's not. There we go. So this guy has some internal symmetry over here, but overall the molecule is not symmetrical. So when I zoom in, I'm going to have this hydrogen. Sorry, palm rejection is being weird. And this hydrogen, and let's call that HA and HB. So HA and HB are on the same carbon, and they're both hydrogens, right? So is there any difference between these two that you can automatically see?
They're in different planes.
They are, but since this is a single, oopsie, since this is a single bond, do the different planes really matter yet?
No.
No, awesome, because it can freely rotate, and since they're both hydrogens, we don't have any chirality to worry about. So can someone remind me what is the definition of chirality, or like what something needs to have in order to be chiral?
Four different groups.
Exactly. So this spot does not have four different groups. However, it does have two different groups and two hydrogens. So this is what we like to call a prochiral or potential chiral center. So what this essentially means is that if we were to replace one of these hydrogens with another group, let's say, I don't know, an oxygen, like an alcohol group, we would get a chiral molecule. For now, you guys don't have to know like what reaction took place or whatever. All you have to know is that in general, if we somehow replaced one of these hydrogens, we would make a chiral center. So does that make sense so far?
Yes, so far.
Yes? Okay, sweet. So my next question to you is, does it matter which one of these hydrogens we replace?
I want to say yes,
Okay. So,
but I
and
don't know.
when I answer like that, it doesn't mean you're right or wrong. It just means I'm going to ask you a follow-up question. So don't get scared. I know it sounded
Okay.
kind of like shady almost. All right. So, let's say we replaced HA in this first example, or excuse me, HB, because we got rid of the dashed one. So let's fill in HA. And then here, let's get rid of HA and keep HB. So this is again chiral. But the groups are flip-flopped. So one of these is going to be R and one of these is going to be S. So if we have two molecules that have one chiral center and are opposite at that chiral center, what is their relationship?
They're enantiomers.
Yes. So these two will be enantiomers. And if anyone remembers from Orgo 1, give me some information about enantiomers and their like chemical and physical properties.
Don't they have the same chemical properties and like the same boiling point and all that fun stuff? There's something that's different though.
Yes. Okay.
I can't
So
remember.
enantiomers have different chiral centers, right? So their optical activity is opposite. So
Oh, okay.
I'm guessing most of us here are in biology, right? Are there any chem majors in here?
No, I'm a bio
So I
major
like
too.
to. You're both chem majors? Wait, what?
No,
Oh.
bio.
Oh, okay. For a second, I was like, whoa. No, I'm kidding. We love everyone here. But since I am also a bio person and most of you guys are bio people, I like to relate things to biology to make them easier to understand. So, if we think in a biological point of view, the difference really between two enantiomers is what they can react with. So, we all know that enzymes are super specific, right?
Hmm.
And so are receptors. So, for example, the receptors in our nose are stereospecific. So, they bind specific enantiomers. So, for example, let's say both of these were going to bind in our nose, right? And they were different smells. This guy would probably have a different smell than this guy because it would be binding to different receptors.
Oh, that's interesting.
Yep. So, a lot of compounds that you guys are probably not going to talk about in this class, but maybe in biochem. The difference between them really is just their chirality. Same thing for medications. You might not have thought of this, but like something like ibuprofen is going to be specifically only one enantiomer because only one of the enantiomers is going to have um, the effect that we want it to. Some drugs can have an enantiomer that is really toxic. Some of them will have an enantiomer that maybe just does nothing at all. So that's why these things are important.
I
Yeah, I
never
And
heard
a
remember
of it
fun
that
Chris.
fact for you
way.
guys.
Yeah, I remember
Yeah,
Chris. That's what I remembered him talking about was the ibuprofen or whatever. That like one enantiomer was like ibuprofen, and then the other one was like toxic or whatever. I think that was the
yeah.
one that he.
I'm glad he talks about it now because I learned about it in a class and I was like, dude, this all makes so much sense now. He was like, yeah.
I love
But
Chris.
yes,
He's great.
he is so wonderful.
He was an awesome
Um,
SI.
right? He's so cool. I try to tell him that all the time. He's like, oh, I don't know, I'm whatever. I'm like,
No,
no.
no, yeah, no. He can't take a compliment. I always try like Chris, just take the compliment, okay? Just say thank you. You're good.
Literally never. If you guys watch the videos on the YouTube channel, he's actually in one of them, which is kind of
Hmm.
funny. Um, so if you see him and you're like, ah, yeah, just that was on purpose, a little treat for you guys. Anywho's, before I completely go off the rails, the reason I bring all of this up, as you said, they have all the same chemical properties, right? Such as boiling point, whatever. That means that when it comes to NMR, they're going to be exactly the same. So you can't look at these two and tell the difference between NMR. They'll be exactly the same. So if we move one step back, these two hydrogens are then going to be enantiotopic. So their relationship to one another, since they form a set of enantiomers, is that they are enantiotopic. And therefore, they will give you one signal, so they will be exactly the same. Um, they just have a fancy name. So nothing is really going to change. There's no important difference between these two other than they have a fancy name. Any questions about an antiotopic?
Nope.
And in case anyone here hasn't heard me say it, there's no such thing as a dumb question. Give me all the questions. I never want you to leave here thinking, oh, I wish I asked that because it didn't make sense.
Right now, I'm
Hello,
just taking
Sarah.
it all in.
That's fair. That's also fair. And plus, um, you can always email me